All right. Hello, everyone. I have about an hour before I need to go somewhere, but I thought to continue with some of the problems of the attention is all you need paper from TensorTonic. I'm really liking just doing these problems and like learning on the fly, even though I'm like not super. Yeah, I mean it's a strange thing, right? Like just speaking to a camera that has like literally nobody viewing it right now. But I mean, it may be the case that in the future people could a future audience could look at these videos to see like at the start of something new, the start of something interesting, the start of something hopefully hopefully what I'm doing right now lasts that long, right? Like because I do have the tendency to pick up something and then drop it um, in as I lose interest in it, right? All right. With that somewhat prelude out of the way, let's start working on today's, or at least the problem that I am focusing on right now, which is the feed-forward network part of the transformer paper. Which just a quick recap of where we are at right now. Let me just share my screen. Yeah, just a quick recap of where we are at right now. We have So in the transformer they introduced like many interesting ideas, right? Like, and the few that we have already been through is like the tokenization, which is the process of converting uh, the body of text into what they call tokens by using a specific algorithm. It could be like byte pair encoding algorithm, and then using those tokens to define the vocabulary of using those tokens to define what vocabulary you have, and the process of tokenization converts those particular tokens of a text into a sequence of index or like numbers, integers really, and those integers are then uh, processed through the embedding layer, which could be like an embedding system that transforms these individual integers into vectors, right? And they're defined by the dimension of embedding, which is usually denoted as d sub e. And then we introduce something called positional encoding, right? So before the body of text, which has been converted into the embedding matrix, is fed into the transformer or like the attention mechanism, you have to imbue the input matrix or like the X matrix with some sense of position, right? Like so the first token should be different from the second token in the sense that like the first token precedes the second token and the third token succeeds the second token, right? Like so there should be a sense of position that the model should learn, and how it is done in the paper is they introduce something called I don't know if it's called anything, but they use positional encoding where they're always they're uh, where they're like generating a sinusoidal position sinusoidal additive based on each, I guess, like it's not really sequence length, is it? It's more no, it is sequence length. Well, I think I need to visit the positional encoding again, but basically speaking, it tries to capture some positional dependencies and adds that or injects that into the input matrix or like the embedding matrix. It gets added into the embedding matrix to become what is called the input matrix, which is usually denoted as X, right? So before it is fed into the transformer, you have X, which the dimensions are like a batch size, and then the sequence length, which is maybe like n, and then you have the dimension of embedding, which is like this d sub e, and then they are fed into the scale dot product attention. And the attention mechanism, how it works is you have basically three matrices that you learn, or like three weights that you learn, set of weights that you learn, which is like a weight of the query, the weight of the keys, and weight of the vectors. Sorry, not vectors, weight of the values, right? Like so, and they are used to generate from the X input matrix. They're used to generate what are called the query matrix, key matrix, and the value matrix, which are generally like the set of query vectors, key vectors, and value vectors that are relevant to us. Then the attention mechanism, how it works is it is generating a probability distribution over all. Yeah, it is generating a probability distribution over all the similarity scores from the query vectors to the key vectors. And essentially how you can think about them is like query vectors are questions that you can ask, and key vectors are like some clues, some hints that may be hidden in a particular token. And the similarity scores are weights of how relevant this particular query key would be to this particular query is to a key. And then what the paper attention is all you need introduces is a scaling factor, which is the square root of dimensionality of the key matrix, or like the key weights. So you basically have, so that's used to generate like the probability distribution over the similarity scores between query and key vectors. And you can think of them as weights for how important, you can think about them as like weights for how important each value vector is. And in this case, the value vectors would be like, okay, what's intrinsically valuable in a particular input matrix, which is X. All right, and then the multi-head attention is what the paper introduces, is like trying to, instead of just having like a main attention block and like a main query matrix, sorry, query matrix and the key matrix and value matrix, you are essentially separating them into like different attention heads, and then like these attention heads would be used to project the query matrix, the key matrix, and the value matrix into the subspace of those attention heads, in which they could like do some proper manipulation, and in which each head could learn, or like could learn a specific pattern in the distribution of the data, and then they are concatenated, and in the process of concatenation, you generate the final output, which would be the concatenation times, or like the concatenated attention scores with the weight of the output matrix, which is usually denoted by like D superscript of O. All right, and that's where we are at in terms of like a quick summary. And now we come into the next stage of the transformer architecture, which is the feed-forward network architecture. And feed-forward networks are usually, I might be wrong, and I might learn as I go on. Feed-forward are usually like just dense linear neural networks, but we'll see. All right, so the problem statement goes like, implement the position-wise feed-forward network from the transformer paper, or attention is all you need. The original paper uses linear layers with a value activation in between. All right, applied independently to each position in the sequence. All right. All right, and the first linear layer projects from D model to a larger hidden dimension D of feed forward, and the second projects back to the D model. In the original paper, D model equals to 512, and D feed forward equals to 2048. Value activation introduces nonlinearity by clipping negative values to 0. Okay, all right, simple enough in terms of the problem statement. Let us go through the theory a little bit more. Yeah, the position-wise feed-forward network is the other main sublayer in each transformer block, paired with multiple multi-head self-attention. It consists of two linear transformations, all right, with a value activation in between. Feed-forward network X, feed-forward network of a given vector X equals to the max of the value function or inner and then the outer. Right, the feed-forward is applied to each position independently, identically acting as per token two-layer multi-layer perceptron that expands the representation to a higher dimension, applies nonlinearity, and contracts back. Okay, we went through this in the original paper of attention is all you need. The model dimension they used was 512, and the inner dimension is 2004 T8. All right, what it is, the position-wise feed-forward network is a two-layer, fully connected network applied independently to the representation of each sequence position. Position-wise means the same weight matrices W1, B1, W2, B2 are shared across all positions in the sequence, but there is no information flow between positions within the sublayer. Each token's demodel dimension is processed in isolation. All right, and that I'm assuming is why parallelism is such a huge advantage for transform architectures. The architecture is straightforward. The first linear layer projects from demodeler to this is pretty much the same. Okay, key equations is pretty much the same. Okay. All right. Batch instrumentation. In practice, the input is a tensor of batch size, sequence length, and dimension of the model, which is generally speaking the embedding dimension. Where B is the batch size, T is again, and this equivalent to reshaping the BT into D model, applying again this equivalent to reshaping to BT into D model. Okay. Why 4 times expansion increases computational capacity? Gives the feed forward a much. So it's the 4 times bottleneck architecture. Expand contract design is a bottleneck. The first projection scatters the input into a diverse set of feature detectors. Value specifies the representation by zeroing out roughly half the dimensions, and the second projection combines the surviving feature back into the D model space. This forces the network to learn an efficient encoding rather than simply memorizing the expanded representation. The 4 times ratio is empirical, which makes sense. The ratio DFF divided by the empirical makes sense, isn't like it's good that there's clarity on it. The ratio DFF divided by D model equals to 4 was chosen to be firm in justice convention models using gated X-weak glue. Example, Llama typically uses 8x3 times D model, which is DFF divided by D model equals to 8x3. The key insight is that the feed-forward network needs a meaningfully larger hidden dimension to provide sufficient capacity, but the exact multiplier is tunable. All right, position-wise application, same weights. The feed-forward network uses the set parameters of every sequence. Position 0 and position 5, 1 are processed by the identical function. Okay. Yep. As we anticipated, because positions are independent within the feed-forward network, all T positions can be processed simultaneously as a single batch matrix multiplication. There is no sequential dependence, making the feed-forward network perfectly parallelizable on GPUs. This contrasts with recurrent architectures where each time step depends on the previous hidden state. Okay, and then why ReLU? And ReLU in particular is a function that for all input greater than 0, it becomes that particular input. For all input less than 0, greater than equals to 0, it becomes was it greater than equals to, or yeah, I mean, I guess it doesn't really matter. Yeah, for every input greater than 0, it becomes that input. Or you can write it as like ReLU of x equals to x if x is greater than 0, elif 0, or else 0. Yeah, without the ReLU or without any nonlinearity in between the layers, they would collapse into a single linear transformation. So it's only learning linear mappings between the input and the output that we want. But it could be the case that we have nonlinearities in the data distribution that we should be able to learn. Residual connection. The transformer adds the residual, which is equals to output, such that output equals to layer norm, and x plus feedforward network of x equals to layer norm of the feedforward networks refines the token opposition when the skip connection preserves the original signal. The input was 4-dimension, expanded to 8-dimension, then compressed to 4-dimension, and huh. Let's see. So the output is the layer norm of x, and in this particular case, what is layer norm? Is it normalizing? Or is it in the letter? Oh yeah, layer normalization comes afterwards. Okay, so the feedforward network's role in the transformer. Attention mixes feedforward network processes. The transformer block alternates between two fundamentally different operations. Multi-head attention allows every position to gather information from all other positions, producing a context-aware representation. In this particular case, the context-aware representation would be the attention scores generated from the input matrix. Then the feedforward network then applies a nonlinear transformation to each token independently. Attention is about communicating between tokens. The feedforward network is about computation within each token. All right, makes sense. The feedforward network has a key value pair. Interpretability research, Jiva et al. 2021 has shown that feedforward networks function as implicit key value memories. Each row of W1 acts as a key that matches certain input patterns, triggering a high pre-value activation, and the corresponding column of W acts as a value added to output when that key matches. Huh. ReLU determines which key are active. This explains why feedforward networks store fractional information in specific W1 rows, detect patterns like the capital of France is, and the corresponding W2 columns push the representation towards Paris. I see. 10 in the base model of the feedforward, 2/3 of the total parameters. Attention has 4 times d square models per layer for query key vector and output rejections, while the feedforward network has 2 times d model times dff, which is 8 times d model square. Huh. The feedforward network is a larger component. I think it's okay. All right, I think I'm mostly there. So to summarize, feed-forward network is a two-layer, two linear layers separated by a value function in between. And what it takes is, so in this particular example, it should intake a x is a vector, right? Okay, we can break it down as a hidden state, and the hidden state is you're expanding the input vector into a higher dimensions space to capture, like, I guess, more information, and use the dimensions to truly separate out. I mean, I'm not sure, but like it probably be the case that you use the high dimensions to really separate out like what information are relevant or not, and then you project it down back into the input, or like the dimension of the model. All right, so let's see. Weight 1 at x. So this is what the hidden state looks like, and then you have define of value of x equals to state. Let's see. Let me just bring some of the test data over. Okay. X equals to numpy dot array. One equals to np dot array. Now b1 equals to np dot array. W2 equals to np dot array. B2 equals to np dot array. Okay, let's see. Let's see. X dot shape. One 114,488. So we need to convert them into Oh, I cannot do that. Let's see what it's trying to do. 11448. So we need 148. All right, let's see. Can we do something like this? Reshape. That's it. Can we do that? So we cannot reshape if it's not already there. That means convert. Or maybe it's not. Take the easy way out for now. Yeah, 114, 181. You1, okay. W1 is 148. Print in state in state dot shape. Okay. Remember. Which makes sense. X is what? X is 114, and then it becomes 144,818. Okay. sequence length into 8. The dimension of the hidden space is 8. And okay. Right. And then do we have, I'm afraid, let me see if I can do this without. Okay, so it works. Let's see. That's interesting. So do we have mv.relu? No. So define a value function. Let's see. Stupid. I see, so it doesn't work. There should be a more efficient way to do this. Yeah, stupid me. Stupid me. Done np.maximum. Okay. All right. And then read hidden state is this activated equals to np relu of hidden state activated state. And then you have the second layer, which is equals to of a second. Yeah. No, we don't have. You might be wondering why I am creating an extra function when I can just write this. But I just like having, I guess, like for clarity's sake, np.maximum for a trained I can see that as like equivalent to the ReLU function, which it is, but most people will know it, will know ReLU first before like seeing this representation of it. So, you know, and for me as well, I just like seeing what actually is happening, conceptually speaking. That's a pain. And hopefully it works. And it does. Right, I have into the next module. Let's see, it's an easy one, so I should be able to do this in a relatively quick manner. All right, so where we are at right now, we have implemented we have retrieved the output by passing in whatever the transform values of that came from like the multi-head attention, and then we fed it into the feed-forward network. And now the process of layer normalization will come. And earlier we had we were eluded in the feed-forward network where we said the final output is the layer norm of x plus the feed-forward, layer norm of x plus the feed-forward of x. And now the question was at that point, like, what is this process of layer normalization and why it might be needed? All right, so let's read the problem statement first, which is implement layer normalization, a technique introduced in attention is all you need. Transformer architecture that normalizes attention across the feature dimension for each individual sample. Unlike batch normalization, which normalizes across the batch, layer normalization computes statistics across features, making it independent of batch size and well suited for sequence models. The formula is layer norm of x equals to gamma of x minus mu divided by sigma square plus epsilon plus beta. And conceptually what it means, mean of x over last axis. And in this particular case, the last axis is almost always the axis on which the dimensions of the model, the hidden dimension, the dimension of the keys, the queries, vectors will be at, right? So it's I guess if you think about it, disregarding the batch dimension, it would be the column dimension, which will be defining the features of the data / the model. All right, gamma is the learnable scale, same shape as last dimension. All right, so that means, okay, that means it's a matrix or a tensor. E is equal to small constant for numerical stability, which makes sense. Sigma square equals to variance of x over last axis. Beta is equals to learnable shift, same shift. Okay, all right. Same as before. Let's touch a little bit on what the theory is. Let's see. So we said the final output will be something like a layer norm of x plus the feed-forward network of x, right? And to recall, feed-forward network of x will be W2 of the value function of W1 x plus B1 plus B2. All right, let's see. We went through this. Normalize the activations across the feature dimension for each. Layer normalization takes a single input vector and transforms it to have a zero mean and unit variance across the feature dimensions. Then applies a learned affine transformation, scale, and learn shift. So this affine transformation is what we had in gamma, right? Like this one. It operates on each sample independently with no dependence on other samples in the batch. In the transformer, layer normalization appears inside every encoder and decoder block. Each block contains two sublayers, okay? Self-attention, which includes the multi-head attention mechanism, and then, which is passed into the feed-forward network, and each sublayer is wrapped into a residual connection followed by a layer normalization. For a 6-layer encoder with two sublayers per layer, that is 12-layer norms operation. The decoder adds a third sublayer, cross attention per block, bringing a total to 18 across 6 decoder layers plus 12 in the encoder. Right, 30-layer norm called per forward pass in the full transformer. All right, so the key equations are: compute the mean across D features, which is fairly simple. You have the sum of the values across the features divided by the number of the features. Computing the variance is all the same. Sum up the difference of the squares of the x values minus the mean. So you need to find the mean first. All right. Normalize each element to have 0 unit. All right. So you normalize. Scale and shift using learned parameters. So what you learn is this gamma vector and this beta shift. This gamma is a vector. It's a learnable scale parameter, and beta is also a vector, is a shift parameter, initialized to zeros, initialized to 1, initialized to zeros. And these are element-wise Hadamard multiplication. Element-wise, that's interesting. Postnorm in the original transformer. The original transformer uses what is now called the postnorm architecture. The paper states we employ a residual connection around each of the two sublayers, followed by the question is, why do you add this one? The computation for each sublayer is layer norm of the output from the feed-forward network and added with the input to the sublayer. So why is it called postnorm? It refers to the fact that normalization happens after residual addition. The residual branch and the skip connection are added first, producing a potentially large and unnormalized sum, and then layer norm brings the combined results back to a controlled distribution. Okay. In the encoder block, the full computation is the hidden state becomes layer norm of x plus multi-head attention of x, 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 where out equals to layer norm. Okay. So in the encoder, you have an extra layer norm in between the self-attention head, or like the self-attention layers and the feed-forward layers. Yeah, each sublayer gets its own. The two layer norms do not share parameters. Why normalize? Is internal covariance shift forces each layer to continuously adapt to a moving target. Normalization fixes the input. Okay. The learnable parameters are gamma, which controls the scale, and the shift, which is governed by beta. Together they form an affine transformation applied equivalent one. Passion introduces paper context, adopts the normalization bar Ross, who produced the best the paper does not do the triggers and no technique, the relevant passage stage, we employ a residual connection now. Okay. Comparison in resonant. Each stacking 6 encoder and decoder would be difficult to train as residual language will accomplish. Alright, numerical example is given post-norm versus pre-norm. The original transform uses post-norm, where the final output vector is given by layer norm of x plus sublayer. GPT-2 uses pre-norm, which is before you feed it into the sublayer, you just layer norm it. The main difference is major consecutive opportunity to gradient flow in post-normal. The gradient must pass through layer norm at every layer in very deep networks. The repeated modification and it can attenuate gradients. The original materials use careful learning rate up. Gradient flow in pre-norm, the residual connection provides a clean identity path. The gradient includes a direct dx by x equals to dx prime divided by x equals to 1, which makes somewhat sense. Yeah, because let's see. Yeah, because there's only an explicit dependence. There's the explicit dependence of x prime on x is 1. Yeah, but here the explicit dependence is not 1. In fact, there is no explicit dependence. So you have to you would have to do chain rule. So d of x partial derivative of x prime divided by partial derivative of x prime with respect to x would be what? Partial derivative of x prime relative to x plus sublayer of x and multiplied by partial derivative of x plus sublayer of x divided by, okay. All right. I think I have enough to start working. Let's see. Same as earlier. Let me just copy and paste the sample starter code. Let me have x gamma beta. Right. Let me just. What? Look how they shine. Look how they shine so bright. Okay. All right. So, all right. What is the x hat transformation? Xi minus mu. Okay. Dot square root of sigma squared plus epsilon. Yeah. Let's see if it works up to this point. Okay, it works. Okay. Or at least it returns a result up to this point. Okay. All right. So the next step is it says element-wise multiplication. So that's a dot product, right? So let's see. Times it. Oh, that's not a dot product. That's a x multiplied by gamma. All right, yeah. 1, 2 is 2. 2, 2 is 4. 2, 3 is 6. 2, 4 is 8. It's probably this one. Return gamma times x hat plus beta. Is that where we're headed? Okay. All right, let's see then. Some tests fail. Which makes sense. X hat. But if x is a vector, I say, or I don't see. Where is it failing? It's failing at a two-dimensional x, which is right. So x is b. Okay. Yeah. Yeah, mu is 2. X is what? X hat equals to x. That doesn't make sense. There must be a way to like broadcast the shape somewhat. Struggling here. Yeah. Oh. Okay. All right, so what were the important lessons here? I needed to be careful in not assuming that X is always a vector, right? X can be a matrix, or, or a matrix of one vector, right? And I also had to be careful in how I was keeping the shapes of the mu and the sigma so that the numpy, I guess, element by element operations or like broadcasting can properly work here, right? Okay. So let's see. I mean, if it may be the case that it's not correct on a grand scheme. All right, that's good. I do think I need to like revisit many of these to really feel like I understand it. I mean, the thing is like you probably never understand it fully, right? Like you can always learn new things. Right. The final thing we have coming up is the encoder block, right? And that's something I'll do in a later session. All right, that's it for today. Or that's it for this session. Well, I had fun learning. I hope you guys did as well. For all the 0 of you that are watching. All right. Goodbye. Goodbye. Goodbye.